All right, so yesterday I had you guys work on the 4.3 review problems after class and work through looking at each of these functions, their first derivative and applying the first derivative test, their second derivative and applying the second derivative test. So I think at some point I goof up and mix up my reds and blues, but I tried for the most part to keep the first derivative in red, second derivative in blue, and the information about them to match as follows as well. So over here to the right, we have all the information that's important about the first derivative. So the first derivative of this function is 2x minus 4. The zeros of this function occur at x equal 2. So then I make my first derivative number line. I check the signs to the left and to the right of 2 and determine what my original graph is doing. So since f prime is negative, the original is decreasing. When f prime is positive, the original is increasing. So that's the key information I have here. Increasing 2 to infinity, decreasing negative infinity to 2. And we have a min at x equals 2. The min at x equals 2 is local because this graph's domain is all reals. We will eventually, or could eventually, prove that it is an absolute. Okay, so that is the first derivative in the first derivative test. Then we want to look at the second derivative. So the second derivative is a constant. So the second derivative is 2. What that tells me is that this graph is always positive. If the graph is always positive, then it is always concave up. And because it's always positive and concave up, that's how we could prove that the x equals 2 on the left is in fact an absolute min because of the concavity that we receive from the second derivative. So that tells me this is concave up always or on all reals. It is concave down never. And we have no points of inflection for that reason. Any questions on that first example? Okay, so example number 2. Its derivative is f prime equals 3x squared minus 30x plus 63. So you have to find its zeros. So I took out a GCF of 3. And then I factored my x squared minus 10x plus 21 to x minus 3x minus 7. That gave me 2 critical points at 3 and 7. So then I did my first derivative test to find where those critical points were positive and negative to the left and right of them. Since it was positive to the left of 3, negative to the right of 3, negative to the left of 7, and positive to the right of 7, that made 3 and 7 both local mins and maxes. So 3 becomes my local max, 7 becomes my local min, and then we have areas of increase and decrease. And again, I tend to make my intervals not including the critical points because those are zeros. And it's not really increasing or decreasing at a 0. Okay, so the second derivative is 2x minus 10. So once again, we find our critical points. So I get when x is equal to 5. I do my second derivative test on my number line. And I have concave down and concave up. And a point of inflection at x equals 5. Okay, so I didn't collect this homework, but what I want you to do now is go to Teams and send me a picture of number 3 and only number 3. So right now, go to Teams and individually send me a picture of problem number 3 because I want to see this one in particular, how we did before we go over it. So guys, go to Teams and real quick, send me a picture of your number 3. And we're going to see a bunch of little purple boxes in that corner. All right, so again, I don't always collect every homework, but I like to see how we're doing. This next question is a question that I think we're very capable of doing, but I also think it's one that could give us some issues. So I want to see just kind of individually how each of us are doing with this. And one way to do that is just to look at one problem. Sometimes I get overwhelmed when I check like 6 pages worth of problems at a time. So today I just wanted to see one problem. So the next example is an example of a square root type problem. So this is actually, if you think about it, the square root of 16 minus x squared. We should know what this is a graph of. What's this going to be a graph of? So think about a formula that has x squared plus y squared equals r squared. A circle. This is the bottom half of a circle with radius 4. This equation represents the bottom half of a circle with radius 4. So right away, I know that my domain of this function are x values such that x cannot be farther apart than 4. Like my range and my domain are going to live in the space between -4 and 4 and so forth. So that leaves that the derivative is -1/2 16 minus x squared to the -1/2. Don't forget the chain rule says take the derivative of the inside. So cleaning that up, I get x over the quantity square root 16 minus x squared. These are going to give the areas where the derivative does not exist. These give the areas where the derivative equals 0. And we already know that the domain is restricted and cannot live between -4 and 4. So -5 and +5 are outside my domain, so I can't have a sign change beyond those. The zeros are going to occur at 0 and positive and -4 because of where the derivative is 0 or does not exist. So we have to look at the sign changes between -4 and 0 and 0 and 4. So it's negative between -4 and 0 and positive between 0 and 4. So it tells me my graph goes from decreasing to increasing. And if I smoothed or made this a little bit more concave up, which we're going to see in the next derivative, you could almost see that semicircle happening on the screen. So again, I just kind of put the information about the domain down here, and I talk about the local mins. Now, because this graph has a restricted domain, EVT applies to this problem. Because this graph has a restricted closed domain, EVT would apply, and we would actually see that these local mins and local maxes are actually absolute min and absolute maxes. So because of the closed domain on this function, these are actually absolutes. Our second derivative of this function is a little bit messier. So you got to do your HODI minus IDO, or you can do a product rule where you kept the square root up top as a negative. So you could do HODI minus IDO, or you could keep the square root as a negative and do a product rule, which is first times derivative of the second plus second times derivative of the first. Either way, you have to come up with a common denominator and clean up some of those pieces. And ultimately, you're left with 16 over 16 minus x squared to the 3/2. Now, can 16 ever equal 0? No, because there's no variable there anymore. So f double prime of x can equal 0 nowhere, because 16 will never equal 0. The second derivative does not exist when the denominator equals 0, which is going to be at that same -4 and +4, which means I just need to find the sign between them. In this case, the sign is positive. Therefore, this is always concave up, never concave down, and no POIs. So G is concave up from -4 to 4. H is no intervals of concave down or none, and there are no POIs. Okay, example number 4. In example number 4, you had two choices to start this problem. You could have distributed the x to the 2/3, or you could do the product rule like I did, because I have a feeling we just didn't distribute. So I chose to do the product rule. I personally probably would have distributed, but didn't think that that was the move most of you would make. So I did not find my derivative that way. I found it taking the product rule. Either way, you're going to simplify down to the same solution set. So we're always looking for zeros and DNEs. DNEs always come from the denominator. Zeros always come from the numerator. So we have a 0 at -12/5 and a DNE at 0. That should make sense to me because we know 2/3 is going to create a cusp. So we know that this graph kind of had that cusp behavior on its original. So I have a min and a max, as well as levels of increase and decrease. Yeah. This one? You can drop it down. For the derivative test, you can, yeah. Because either way, like the bottom isn't going to be affected by it, and then top ends up not being affected either. Yep. All right. The second derivative is a little messier. And my handwriting was a little messier because of the iPad, so I apologize. But that's a negative 4/3. That is a negative 4/3. So you have x to the negative 4/3 out in front, and then it simplifies to 10/9 x minus 4/3 on the inside. So this would drop to my denominator and be my DNE. This is going to be my numerator and give me my values. So you have 10/9 x minus 4/3 equals 0, and x to the negative 4/3 equals 0, which we know the DNEs are going to be at 0. And then we get 6/5 over here. Now that DNE this time, and this should make sense, because again, I keep stressing it's a cusp. So cusps look like the little winged birds that are like your graphs. So it should make sense to us that there isn't a concavity change at a cusp. It's just that point of non-differentiability. So the graph is kind of like going in and then coming back up without changing concavity. And then it does change concavity at 6/5. Okay, and then the second thing we worked on was writing justifications. So we wrote justifications for that handout that I gave you. And again, you were taking in these graphs and interpreting what was happening on those graphs. So in a little more, I think that still gives you every answer if I do that. Like I said, sometimes like NIMSY, they're going to make their intervals bounded. I make mine parentheses for the most part. That's one area for increasing and decreasing they're a little less picky on. But you can see even here, NIMSY keeps their increase and decrease as parentheses and not brackets, just like I do. These statements here, x equals -6 and x equals 9.5, because f prime changes from positive to negative at these values. That is what we are looking for these descriptions. Can you tell me what is happening on the derivative to make the original be that? Let me go back up to the graph. So the graph, is she answering? Did she answer or do you need me to answer it? Thanks for listening. All right, and then part 2. So one of the things in part 2, you'll notice they put somewhere in your paper you should write f prime of x equals g of x. Typically on a free response question on the AP exam, they want you at some point to make that connection. So you could use either function interchangeably. So here it could be because f prime of x is greater than or equal to 0. Or you could have said because g prime of x, or g of x rather, is greater than or equal to 0. As long as at some point you make the connection and understanding that f prime of x is g of x. Okay. So when we come back at the end of the day, I've been debating whether I want to go to optimization or related rates. I think we're going to go to optimization because that's about maximizing and minimizing functions. So that kind of summarizes how the derivative affects the shape of the graph. Tomorrow we're going to investigate shapes of graphs. We're going to maybe sketch some graphs and continue with looking at maximizing and minimizing. So optimization is about finding the max and the mins for word problems. So that's what we're going to pick up with this afternoon when we see each other again.